Hello, welcome to another module in this massive online course on Bayesian MMSE estimation for wireless communication systems. Alright, so we have looked at the model of an intersymbol interference channel, alright, model of a wireless channel with intersymbol interference, and we also said that removal of intersymbol interference is termed as equalization, alright. So now let us look at, in this module let us look at LMMSE or MMSE based equalization for a wireless communication system. So what we are going to look at starting this module is basically LMMSE equalizer design. So basically equalizer or design of an LMMSE equalizer for wireless channels. We are going to look at a design of LMMSE equalizer for wireless channels, alright. So towards this end, for this purpose, consider a 2 tap. If the number of taps is L, consider an L equal to 2 tap consider an L equal to 2 tap wireless channel. Therefore, we can express, since there are 2 channel taps, we will have Yk equals H0 times Xk plus H1 times Xk minus 1 plus Vk, correct. So these are the 2 channel taps H0 and H1, these are your 2 basically coefficients of the channel filter, these are also termed as their channel taps. Xk is the current symbol, alright, at time instant k. Xk minus 1 is the previous symbol at k minus 1. Okay, the previous symbol from time instant k minus 1. So Xk minus 1 is causing interference to Xk, alright. In Yk we have contributions from both Xk as well as Xk minus 1, and this is what we termed as intersymbol interference. Okay. So this interference is what we termed as ISI or intersymbol interference, and removal of ISI is termed as, so this is your noise, Vk is of course noise or rather additive wise Gaussian noise, and removal of ISI or basically intersymbol interference is termed as removal of intersymbol interference is termed as equalizer, and we want to design an equalizer towards this process of to perform equalization in this wireless communication channel, thereby removing the effect of intersymbol interference, alright. So now let us design, for this purpose let us consider the design of a 3 tap equalizer, which means we will consider Yk, Yk plus 1, Yk plus 2. So let us design a 3 tap equalizer. So we will consider the design of a 3 tap equalizer considering Yk plus 2, Yk plus 1 and Yk, 3 tap equalizer, and the system model, the model for this can be expressed as, alright, these are the 3 output observations that we are going to consider at time instant of course at time instance k, time instant k plus 1, time instant k plus 2. The model for this can be formulated as let us formulate the model for this, that will be yk plus 2, yk plus 1, yk. These are the three symbols at time instance k, k plus 1, k plus 2. Let us call this as y bar k, that is a vector y bar k. This you can see can be expressed as, from the model for the intersymbol interference wireless channel, this can be expressed as H0, the matrix H0, H1, 0, 0, 0, H0, H1, 0, 0, 0, H0, H1 times xk plus 2, xk plus 1, xk and xk minus 1 plus the noise vector. Of course, we have the noise vector which is Vk plus 2, Vk plus 1 and Vk. Okay. And of course, for instance, you can verify this as Yk plus 2 equals H0 times xk plus 2 plus H1 times xk plus 1 plus Vk plus 2 and so on. Alright. So, we can denote this by this matrix by H, this is the effective matrix. Okay. This matrix by x bar k and this matrix and this vector rather by v bar k. So, we have this model considering model for k, k plus 1, k plus 2 can be expressed as, we have y bar k equals, this is the model that we have developed for a 3-tap equalizer, equals h times x bar k plus v bar k. Okay. So, this is the model that we can derive for this, that is your y bar k, where y bar k consists is a vector consisting of observations yk, yk plus 1, yk plus 2, alright, or rather it is a vector which yk plus 2, yk plus 1, yk in that order equals the matrix H times the vector xk plus 2, xk plus 1, xk, xk minus 1 plus the noise vector vk plus 2, vk plus 1, vk. Okay. And from this basically, now from this vector yk plus 2, yk plus 1, yk, basically based on this observation vector we have to estimate xk, that is a process of equalization. Okay. So, that basically you are removing the effect of xk plus 1 and xk. So, from yk, so from y bar k estimate xk thereby removing effect of xk plus 2, xk plus 1 comma xk minus 1, and this is basically your equalization. By using yk plus 2, yk plus 1 and yk, basically we are trying to recover xk and remove the effects of the other symbols, other interfering symbols, which in this case are xk minus 1, xk plus 1 and xk plus 2. This is the equalizer, this is the concept of equalization, and we will use the LMMSE principle to derive the equalizer, alright. And therefore, naturally what we have is, let us start. So, first, so naturally the LMMSE estimate or the LMMSE equalizer is given as, we already know this, x hat of k will be r x k y bar k, the cross covariance between x k and y bar of k, times r the covariance matrix of the observation vector r y bar k inverse times y bar of k. This is the LMMSE estimate this is the LMMSE estimate of x of k, alright. And towards this end, basically we have to derive these two quantities r x k y bar k, the cross covariance, r y bar k, the covariance matrix of the output vector y bar k. Now, for this let us consider the standard assumption, that is IID symbols x k. So, consider IID, that is independent identical symbols of x k with mean 0 mean equal to 0 comma power equal to PD. Okay. Consider IID symbols. We are considering the transmitted symbols xk to be IID, that is independent identically distributed with mean 0 and power PD. This means, therefore, again this is also straightforward, that is expected value of x of k, each symbol x of k equals 0, expected value of x square of k, which is the power, this is equal to PD, and expected, since the symbols are independent, expected value of x k into xl equal to 0 if k is not equal to L. Now, what we want to do is basically, now let us start by looking at expected value of x bar k into x bar k transpose. Remember, x bar k, this is the vector x bar k. X bar k is the vector that is different from x k. X bar k is this vector which contains x k plus 2, x k plus 1, x k and x k minus 1. Okay. So, something to keep in mind, that x bar k and x k are slightly different. Okay. X bar k is the vector which contains x k plus 2, x k plus 1. So, this x bar k contains the vector x k plus 2, x k and x k minus 1. Okay. That is your vector x bar k into its transpose. Okay. And the transpose will be x k plus 2, the row vector, same vector, but the row vector. X k, the minus 1. Now, this will be equal to expected value of x square, of course, the diagonal element will be x square k plus 2, x k plus 2, x k plus 1, x k plus 1, x k plus 2, x square k plus 1, so on and so forth. And now, if you can see, the diagonal elements are going to be x square k plus 2, x square k plus 1, x square k minus 1. Expected values of the diagonal elements are each PD. But if you look at the off diagonal elements, they will be of the form expected value of xk, expected, for instance, expected value of xk plus 2 into xk plus 1, and expected value of xk plus 2 into xk plus 1 is 0, because the different symbols are independent. So off diagonal elements, these elements will go to 0 once you take the expectation, that is important. Once you take the expectation operator inside, and these will be equal to each equal to PD. So this will be a diagonal matrix with PD on the principal diagonal. So this is basically going to be PD times identity matrix, that is basically your expected value of x bar k into x bar transpose of k, that is considering IID, independent identically distributed elements. We have expected value of x bar k, x bar transpose k is PD times identity matrix, where PD is the power of each symbol. Okay. Now let us now look at, come to R, like we have computed so many times before, the covariance matrix of the output vector y bar is expected value of y bar k y bar transpose of k. This will be your expected value of h x bar k plus v bar k times h x bar k plus v bar k transpose, which is equal to expected value of h x bar k plus v bar k into x bar transpose k h transpose plus v bar transpose k. Okay. Now what we are going to do is also assume the standard assumption, assume symbols, each symbols XL comma noise VL are uncorrelated. In fact, they are independent. So let us assume they are independent. All right. For us, we need only the. So in reality, the symbols from the transmitter, the symbols are transmitted by the transmitter, and the noise is at the receiver. So these two processes are different processes, and therefore these two are independent. Let me write this again clearly. So let us assume, so these two are independent, and therefore naturally what we are going to have, if we assume 0 mean noise, expected value of x bar, or even otherwise expected value of x bar k v bar transpose k equals 0, expected value of v bar k x bar transpose k both of these things are 0. And therefore now what we are going to have is, if you expand this covariance R y bar k, what we are going to have is expected value of, we are going to have expected value of h x bar k x bar transpose. So we are going to have expected value of, so if you expand this h x bar k x bar transpose k into h transpose plus the next term will be h x bar k v bar transpose k h k v bar transpose k plus v bar k x bar transpose k h transpose plus v bar k V bar transpose k, and now splitting this expectation operator, we will have x h expected x bar k, x bar transpose k, h transpose plus h expected x bar k, v bar transpose k plus expected v bar k, x bar transpose k, h transpose plus expected v bar k, v bar transpose of k. So, this is what we have once we expand it into the expectation of the separate terms and take the expectation operator inside. And now let us simplify each term. Now we know expected x bar k, v bar transpose k, this is 0, these two terms are 0. Of course, assuming IID Gaussian noise samples of mean 0, variance sigma square, we have already seen this is sigma square times identity. This assuming IID symbols of power PD, this is PD times I. So, this net matrix becomes PD H transpose plus sigma square I. Okay. So, let me just clarify that once more regarding the noise covariance. I am not repeating since we have seen this many times before. Expected value of V bar k, V bar transpose k equals sigma square I. This is assuming 0 mean IID Gaussian noise samples of power sigma square or variance sigma square. So, R y bar k, y bar k, the covariance matrix of y bar, that is basically PD H transpose plus sigma square times identity. We have computed the covariance of the output, Of course, H is the effective matrix for the ISI channel. Effective matrix for the ISI channel, and this is the structure of H. Alright, if you don't, you can recall that this is H, which is the effective matrix of the ISI channel. And realize this effective matrix for this ISI channel depends on a couple of things. One, it depends on the number of channel taps, alright, and two, it also depends on the order of the equalizer, that is the size of this effective channel matrix X depends on the total number of taps in the channel. It also depends on the number of taps in your equalizer. Okay. So, basically this is the effective channel matrix H, and now let us look at the cross covariance between xk, not x bar k, but rather xk, the desired symbol to be estimated. So, now let us look at R xk y bar k, that is expected value of the symbol xk times transpose of the vector y bar k, which is expected value of xk times h x bar k. This is different, this is x bar k plus v bar of k, okay, and this is now equal to expected value of, let us write this down as xk x bar transpose k h transpose plus v bar transpose k which is equal to expected value of well x k x bar transpose k into H transpose plus expected value of x k V bar transpose k. Now, basically again we know the noise and symbols are uncorrelated or independent, therefore, this is equal to 0. So, what we are left with is expected value of x k x bar transpose k times H transpose. Now, let us explore this quantity. Let us explore this quantity, expected value of x k into x bar transpose k. This is equal to expected value of well x k, the symbol x k, times the row vector x bar k x k times x k plus 2 x k plus 1 x k into x k minus 1, which is basically expected value of course. Now, if you expand this, you can see this is x k. If you expand this, you can simply see that all the terms except the expected value of x square k, those will vanish. Expected value of x k into x k plus 2 is 0, expected value of x k into x k plus 1 is 0, expected value of x square of k is p d, expected value of x k into x k minus 1, this is 0. So, this is equal to p d into 0 0 1 0, and we will denote this matrix as vector 1 bar 2 transpose. Okay. So, this we can call it as P d times 1 bar 2 transpose, because if you look at this vector 1 bar 2, the definition 1 bar 2 is 0 0 1 0, and if you start counting from the first position as 0, this is the 0th position, this is the first position, this is the second position, and this is the third position. So, this vector 1 bar 2 has all zeros except 1 in the second position. So, if you look at this vector 1 bar 2 that we have defined, this is all 0 vector except it has 1 in the second position, alright. So, this is a vector 1 bar 2, and naturally therefore, now this is P d times 1 bar 2 transpose. So, this will be your P d 1 bar 2 transpose times H transpose. Therefore, finally, what we have is R, the cross covariance R x k y bar k is P d 1 bar 2 transpose into H transpose. This is the cross covariance, and now we can find the estimate. Finally, the MMSE equalizer, the LMMSE equalizer. X hat of k equals R x k y bar of k into R y bar of k inverse into y bar of k, and therefore, x hat of k equals P d 1 bar 2 transpose H transpose into P d H transpose plus sigma square identity inverse into y bar of k, and therefore, this is your expression for the neat elegant expression. So, this is the LMMSE equalizer. For your wireless. So, this is the LMMSE equalizer for the wireless channel. And a couple of points before we conclude. Basically, though we have illustrated this for a simple case with 2 channel taps and a 3 tap equalizer, as you can see, you can naturally extend it to a scenario with any number of channel taps and equalizer of any order or any number of taps in the equalizer. All that changes is basically the effective channel matrix has to be appropriately constructed for the FIR for the channel filter with the given number of channel taps and the equalizer of the desired order. Alright. So, this can be naturally extended, and 2 also again we have considered a simple scenario with IID symbols, but if there is in principle, if there is, that is if there is some correlation between the different symbols, that also can be handled, because what changes is basically only the covariance matrix, that is expected value of x bar k transpose. Alright. If you construct the covariance matrix appropriately and plug that in basically all the expressions, that we can handle even the case where the symbols are correlated and so on and so forth. So, this basically illustrates a simple example or a simple scenario of LMMSE equalizer design for 2 channel taps and 3 tap equalizer. Alright, and this can be readily extended to other scenarios very easily. So, this illustrates basically the concept of LMMSE equalizer design and LMMSE equalization for a wireless communication channel with intersymbol interference. Towards basically the equalization is towards removing the effect of intersymbol interference. So, we will conclude the module here. Thank you.